Today I will see some example of linear transformation which had come in different type of competitive exam. And this example had come CSIR net 2024 June exam. The question is, here the linear transformation where the kernel is equal to image. That means T be a mapping from vector space to vector space and kernel equal to image. Then first option, the dimension of T is even, obviously, because since T be finite dimensional vector space, so we all of us know dimension of card T plus dimension of image T equal to dimension of V. Since kernel and image both are equal, so we can write this as dimension of card T plus dimension of card T equal to dimension of V. So this is equal to 2 dimension of card T equal to dimension of V. And since here the even number, so obviously the transformation T is even. So option 1 is a right option. Next, the question about the trace of T is 0. Trace means here the question about the eigenvalue, because we all of us know sum of eigenvalue is called as trace. Since here kernel T equal to image T, therefore if lambda be an eigenvalue of this linear transformation, that means there exists non-zero V such that TV equal to lambda V. Therefore that implies TV belongs to range of T, and since range T is equal to null space of T given, therefore actually lambda V belongs to null space of T, that imply T lambda V equal to 0. That imply lambda times TV equal to 0. And since lambda times TV equal to 0, that imply either lambda equal to 0 or TV equal to 0. But TV equal to 0, that imply lambda V equal to 0, which is equal to lambda equal to 0. I hope my all viewers have understood this is. So when the range T and null space both are equal, then actually the eigenvalue is 0. And when the eigenvalue is 0, then we all of us know that operator is nilpotent operator. That means this type of operator, when null space and range space are both equal, this type of operator is called as nilpotent operator. So trace of T is 0, obviously this is true. Third option, the minimal polynomial of T cannot have two distinct roots. Obviously this is also right option, because here only root is 0. And option 4, the minimal polynomial of T equal to the characteristic polynomial of T. Is it true? If the operator is nilpotent operator, then there exist many examples whose characteristic polynomial is not similar to minimal polynomial. because nilpotent operator is not diagonalizable. And when diagonalizable, when the operator is only zero operator, but here operator is non-zero operator, so this is not be diagonalizable. Since this is not be diagonalizable, so minimal polynomial cannot equal to characteristic polynomial. Just see one example. As for example, let's consider this matrix. Here range T is 1 0 0 0 1 0 0, and null space is obviously this equal for null space x1 x2 x3 x4 equal to 0 0 0 0, and that imply x1 equal to 0, x2 equal to 0, and x3 x4 are arbitrary. So null space would be 0 0 1 0 0 0 0 1. Notice here range space and null space both are equal, so we can consider this type of matrix, but its characteristic polynomial would be cat t is equal to x to the power 4, but minimal polynomial of t is actually x square. So here minimal polynomial is not equal to characteristic polynomial. Actually, since the operator is nilpotent operator, so it is not diagonalizable, and when operator is diagonalizable, so then minimal polynomial always equal to the characteristic polynomial. And since the not diagonalizable, so actually minimal polynomial cannot equal to the characteristic polynomial. So option 4 is a wrong option. Next question, which had come CSIR NET 2024 June exam. The question, T be a linear map with 4 distinct eigenvalue, which satisfying this operator t to the power 4 minus 15t square plus 10t plus 24i. That means t to the power 4 minus 15t square minus 10t plus 24i equal to 0. This is be the annihilating polynomial of this operator, which has distinct eigenvalue, which has 4 distinct eigenvalue. Now notice the option, which of the following statements are necessarily true. Option 1, there exists a non-zero vector v1 belongs to R4 such that tv1 equal to 2v1. Option 2, there exists a non-zero vector v2 belongs to R4 such that tv2 equal to v2. Option 3, for every non-zero vector v belongs to R4, the set 2v, 3v is linearly independent. Option 4, t is 1 1 function. This is very easy question. This operator has 4 distinct eigenvalue given. At first, solve this operator. Here the annihilating polynomial is x to the power 4 minus 15x square plus 10x plus 24i equal to 0. 24 equal to 0. This is the annihilating polynomial. Then solve the equation. You will get, if we solve this polynomial, then you will get, after solving, the polynomial would be such type x minus 2x times x plus 1 times x plus 4 times x minus 3 equal to 0. If and we all of us know the minimal polynomial always divide the annihilating polynomial. Then possibility of minimal polynomial either x minus 2 or x plus 1 or x plus 4 or x minus 3 or x minus 2 x plus 1 or x plus 1 x plus 4 or x plus 4 x minus 3 or x minus 2 x plus 1 x plus 4 or x plus 1 x plus 4 x minus 3 or x minus 1 sorry x minus 2 x plus 1 x plus 4 x minus 3. From this, if this is the minimal polynomial, then characteristic polynomial would be x minus 2 to the power 4. That means the eigenvalue would be 2, 2, 2, 2. This is cannot possible, but because here given this operator has 4 distinct eigenvalues. If we consider this is be the minimal polynomial, then characteristic polynomial would be x, possibility of characteristic polynomial x minus 2 whole cube x plus 1 or x minus 2 whole square x plus 1 whole square or x minus 2 x plus 1 whole cube. This is the possibility of characteristic polynomial. Notice, for this possibility there does not exist distinct eigenvalue. So only possibility is this. For this possibility there exists distinct eigenvalue. These are 2, minus 1, minus 4, 3. Only this possibility always we will get distinct eigenvalue. Otherwise this is not possible. So minimal polynomial is this. That means if this is the minimal polynomial, then eigenvalue are 2, minus 1, minus 4, 3. Okay, and if 2 is the eigenvalue, then obviously we all of us know if lambda is the eigenvalue, then TV equal to lambda V. Since here 2 is eigenvalue, so obviously there exists one vector V1 such that TV1 equal to 2 V1. So option 1 is the right option. Another method, if you don't solve, if you cannot solve this operator in this way, here given TV, there exists a non-zero vector V1 belongs to R4 such that TV1 equal to 2V1. That means 2 is an eigenvalue. If 2 is an eigenvalue, then these two always satisfy this operator. Notice here would be 2 to the power 4 means 16 minus 15 times 4 plus 10 times 2 plus 24, which is equal to 0. So obviously 2 is an eigenvalue. Next, notice, given there exists a non-zero vector V2 belongs to R4 such that TV2 equal to V2. Is it possible? Notice, here the eigenvalue is minus 1. But if TV2 equal to V2, that means the eigenvalue is 1. But here, for this operator, there exists one eigenvalue minus 1. What eigenvalue of this operator? Okay. That means Option 2 is wrong option. Also, if we consider 1 with the eigenvalue, then obviously similar to before, 1 would be satisfy this operator. But notice 1 means if we say put this value here, 1 minus 15 plus 10 plus 24, and this value would be 11 plus 9, which is equal to which cannot be equal to 0. So 1 cannot be eigenvalue. This is the easiest way. If you cannot solve this operator in such a way, then this is the easiest way. Because if 1 be the eigenvalue, then always this is satisfy this polynomial. And option 4, t is 1 1 function. Obviously t is 1 1 function, because here all eigenvalue are distinct and non-zero. So determinant of t is not equal to 0. So t is obviously 1 1 function. And option 3 imply for every non-zero vector v belongs to R4, the set 2v1 and 3v, the set 2v, not v1, 2v comma 3tv is linearly independent. We all of us know linearly independent means the set 2v 3tv linearly independent means there exists c1 2v plus c2 3tv equal to 0, and that imply always c1 equal to c2 equal to 0. Is it possible? Then we can tell this set is linearly independent. But, and here tv means lambda v, and this is true for all v. Since 2 is an eigenvalue of this operator, that means tv equal to 2 times b. This is possible. Consider for this eigenvector, restrict one eigenvector to tv1 equal to 2v1. Then put the value, then this would be c1 times 2v1, because here I have restricted v1 with the eigenvalue, plus c2 times 2v1 equal to 0. Here if we put, this would be 6v1 equal to 0. That imply, this imply c1 v1 plus 3c2 v2 equal to 0. Sorry, here v1 equal to 0. That imply c1 v1 equal to minus 3c2 v1. Or we can write this as c1 plus 3c2 times v1 equal to 0. And since obviously v1 is non-zero eigenvector, so obviously v1 is not equal to 0. That imply c1 equal to minus 3c2. By this expression, we cannot tell c1, c2 equal to 0. So, for this eigenvalue, tv1 equal to 2v1, for this eigenvalue 2, I have got this set is not linearly independent set. So option 3 also wrong option. Only option 1 and option 4 is the right option. I hope my all viewers have understood this type of question clearly. Okay? Oh well. I will stop here. In my next video, I will discuss different type of question of linear algebra, because linear algebra is very important for any competitive exam. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.